Alright, well, welcome to 2.1, Rates of Change in Limits, Day 2. Okay, today we're going to study the properties of limits. We're going to talk about how to evaluate a limit algebraically. Last time we saw the limit evaluated using a table, and we had a visual idea of what a limit means based on a graph and looking at points in a certain locale. Okay, so let's take a look. I want to zoom in on these properties and we'll just go through them real quick. Okay, there's not a lot to say. The first one is pretty much formulaic, and a lot of these are, you can just kind of follow them as if they were rules, but they all have actually to do with the shape of the function itself, and I'll make some brief comments as we go on through these. I'll zoom back just a bit. Okay, so first of all the ones we're doing are what we call finite limits. So the limits are as x approaches c, c being some real number, an x value. Okay, so the first one is a constant function. So we've seen many things in this position already. We saw sine x over x. We saw x cubed minus 8 over, I think it was x minus 2, and such. So this particular one would be as if you just had a constant there. Turns out that finding a limit as x approaches c for any given constant function is exactly that constant. So an example of this would just be simply, if you're doing a limit as x approaches 10 of the function 5, f of x equals 5, well, the answer is 5. So it comes out to be 5. Okay. Conceptually, this is actually a pretty good example to understand what's going on. We're dealing with the graph itself being simply the f of x equals 5 line, constant linear function. And you're actually out here at 10, and you're studying the graph's y value in points, at points that are near x equals 10. So whether you're coming from the left or the right, this is a line, and all the y values are 10. So it's a moot point to be even asking this question. Okay, so it's just 5. I hope that was clear. Okay, let's go back to this one. This is actually also a simple function. This is a function you should know, and that's the y equals x line. So I'll do an example over here. I don't want to use up all my space. Well, let's say you want to do x approaches 2 of x. Well, what you have is the y equals x line. I guess I should show you what I'm drawing here. Okay, so you can write that. Sorry, I blocked it. Okay, so this is the y equals x function. F of x equals x. It's just a linear function. Slope 1 passes through the origin. So if you come over here to x equals 2, y is equal to 2. And that's true as a limit as well. We're going to talk about the fact that if a graph is completely continuous and passes right through a point, 2, 2, then its limit is also 2, 2, provided the graph is defined over the interval, not just at the point. But that doesn't need to make sense too perfectly right now. The point is, this is akin to plugging into. So it's kind of like plugging into for x. But you could also just memorize it as, this is the line. Every x coordinate matches up with the y coordinate. So if you're at 2 or near 2, the y value is at 2 or near 2. And we emphasize the word near here, not at, because we're doing limits. Okay. The following phrases, the limit of the sum is the sum of the limits, and the limit of a difference is the difference of limits. It's just a vernacular way of expressing the following facts. Okay, so you'll notice I use the cursive on this. The limit of two functions added is the sum of the two limits evaluated separately. Now I didn't put my value in here yet, so we'll go back and do that in a minute. And since we're just dealing with any value for our limit, this applies to any value here. I think of this as just distributing the limit symbol. It's just how my mind works. But what's really going on here is you're just stating basically that if you have a function made up of a sum of two functions, then you can evaluate the two functions separately and then add them, rather than adding them first and then evaluating the limit. The same rule holds true for a minus sign, so you can just write that in here. The limit is x approaches c. Okay, then this one would be f of x minus g of x. And we can split that into two limits, a difference of limits, see? And this rule is very flexible and forgiving. We can apply it to multiplication, constants, multiplication. So in other words, product of two functions, product of a constant and a function, and also quotient and powers and roots. So we're just going to speed this up a little. Okay, so the limit of a product is the product of the limits. The limit of a constant. Okay, so for a constant we can pick any value or any variable. I probably don't really want to use c again, so I'm going to go ahead and use k. I'm not sure what the book uses, doesn't really matter. So we'll say the constant is k. Basically what this is allowing you to do is factor out that k, or if it's already factored out, you can bring it back in. So it would look like that. That's kind of a neat rule, and you will definitely find yourself using that. Okay, the next one is the limit of a quotient is the quotient of limits. Okay, so this is just analogous to the one we did a minute ago with the product back on number 5. Now this of course assumes that g of x is not the zero function. Got to write a little bit smaller here. This would be limit of f of x, and then this is divided by limit of g of x as x approaches c, and this of course is implying, or this requires that g of x is not the zero function. Okay. Okay, rational power. Rational just means a fraction, remember? So we're dealing with fractional powers. I just want to remind you that when you have a fractional power, it actually represents both a radical and it also represents an exponent. So it's both. It's a base. So the base will be our function, basically. So we're doing a limit, first of all. Alright. Okay, and then we have our function. This time the function has an exponent on it, so it doesn't really matter exactly what we call it. How about we pick our m over n. Again, I'm not sure what the book uses here. Okay, so we're just checking something on my computer there. Okay, so m over n, and then this allows us to basically take the limit of the function and then take that answer and raise it to m over n. So what you see right now is actually the function with the m over n power on it. So you can, I guess, put on extra brackets here. Look a little ugly, but something like that. And then you could have instead the limit as x approaches c of f of x here, see? And then do the m over n exponent out here. Okay, So all these rules should be practiced here. So let's just go through one at a time and look at them. Alright, so see this first one? This allows us to use rule 3 from up above and split this into 3 separate limits. Okay, so you can see I split this up into 3 limits. I actually just used rule 3 to split this part up into a sum, and also had this minus 4, so I had to exercise rule 4 from up above, where the limit of a difference there is a difference of limits. So you can see how this all split up. Okay, see this? This can be written also as the limit as x approaches c of x with a square on it. See, there I just exercised my rule 8. Okay, let me show you what I'm writing here. Okay, now I've got the remainder of this. I haven't changed it yet. I like to do things in stages. I don't see any real rush when I'm teaching this. Okay, so each of these has its own method. So remember, the limit as x approaches c for x is simply c. So we end up with c squared. The second one is c. And we said that for a constant, we just go with that constant. So the answer is c squared plus c minus 4. Now our work on this is completely overkill. I mean, if you look at the original problem and you had just plugged in c to begin with, you would have gotten c squared plus c minus 4. So why did we go to all that hassle to split it all up? Well, this is just a chance to show you that these rules do work, that if you were to draw the graphs of these various things, you would find this to be the case. In any case, you have my full permission to now plug in the c from the get-go, but at least you've seen the work that leads to it. Okay, and see, this one would be the same way. It's a separation into 3 limits. It's basically an opportunity to use both rules 8 and 1 and 2. 8, 2, and 1, actually, in that order. So this time we're plugging in 5, so the answer is literally 5 squared plus 5 minus 4, which gives us 30 minus 4 is 26. Pretty basic. Okay, and this one actually would work as well. You could distribute it and you're good to go. Or just for fun, we'll go ahead and show a little extra work on this. There's that one, which we worked out earlier, times, and then we're going to do the limit on that x minus 2 separately. Okay, so this first part is 5 squared, and the second part we can break this up. I'm showing too much work, but oh, sorry, I didn't show you what I was doing there. Yeah, I'm splitting this up into 2 separate limits. Like that. So I just inserted the 5 squared because I did that earlier. And then here I did a split. You don't have to show this much work. But don't be surprised if the book does. So this comes out to be 3. So it's 75 in the end. Okay. So there it is. Pretty basic stuff. Alright, and what about this one here? We've got to treat this one with a little more respect here. Do we really want to just plug in numbers here? Okay, well, if you look at this one, it does kind of resemble the one I had you memorize last time. So, how is it different? Well, it's got the tan x on the top. Okay, so let's take a look at that. Okay, we could draw the graph for this, and the book does that. The book actually shows the graph for this. But we don't have to. We can actually use the property or the rule that tan x represents sine x over cosine x. So first thing I'm going to do is split this up. I'm going to put the x goes to 0 here. Okay, I'm going to write this as limit of tan x, and then divided by, we'll draw that under here. Like that. And then we'll go ahead and put in sine x over cosine x here. And this goes to 0. Okay, you notice I can't really plug in 0. You know, if you were thinking maybe we just plug in 0 to begin with, you do get tan 0 over 0. Tan 0 is 0, and of course x is 0 when you plug that in. So you end up with 0 over 0, which is actually undefined. So don't think of that as 1 or something you can cancel, or 0. 0 over 0 is undefined. I don't know if I mentioned that before. Okay, well, I don't have any problem plugging in x equals 0 here. Cosine of 0 is actually 1. So I don't have any problem with that. It's this division by 0 down here that's a bother. So I'm going to go ahead and regroup this a little bit. So I'm going to go ahead and write this as limit as x goes to 0 and then I'm going to put the sine x with the x, and I'm going to separate that 1 over cosine x that's in there onto its own limit. So I had a feeling this sine x over x could play a role somehow in here. Okay, so I've separated into 2 limits. This one I've memorized, you've memorized from the last lesson. And this one I can literally just plug in 0. So I get 1 over 1. Okay, so you say, well, Mr. Shore, the answer is 1. I could have plugged in my 0 to begin with. I would have had limit as x goes to 0 of 0 over 0. In other words, the answer is 0 over 0, which is 1. But 0 over 0 is not 1. It isn't 1. So you can't do that. And if you were to confirm this graphically, if you were to look at the graph, the book does this. But yeah, you can see the graph is actually where there's asymptotes here at pi over 2, if you remember your tangent function. By the way, those tangent graphs and secant graphs and such do play a role in this course, so make sure you keep those handy or know how to graph them quickly on your calculator. Alright, so here's your graph, basically, and there's asymptotic behavior everywhere, but we're really interested right in here. You can see that as you come in from the sides, either way, from either side, your limit is 1 on that y value. This is the graph not of tangent, but of tan x over x. So you'd have to maybe enter that on your graphing screen. y1 equals tan x over x. I'll close out that parentheses there. Okay, so much for that. Okay, there is another topic here, one-sided and two-sided limits. Okay, so we call the limit of f of x, the limit as x approaches c from the right, well, what do you suppose we call it? The right-hand side limit. Okay, so we have the right-hand limit, the left-hand limit. Sorry, the zooming might be a little bit of a problem with lessons, but I'll talk through it too, so if you hear me talking, but I don't shift it quite right, then I'll fix it and pause for a minute. Okay, so this says right hand limit. Okay, and the limit of f as x approaches c from the left, we call that the left-hand limit, of course. The naming is very important here. All of these phrases are important. Like any other class you take, vocabulary is actually very important here. Okay, and then to denote that we're not doing a general limit, but a limit from one side, we use these plus and minus superscripts on our value of approach. So you can see here that the plus actually refers to a right-hand limit, and the minus to a left-hand limit. One of the things that's a little bit annoying is that in order to do a right-hand limit, you need to approach it from the right going leftward. So some people confuse that minus or that plus, assuming it should be minus because you're actually sliding to the left toward that c value. But nonetheless, you're studying the right-hand side of the graph, so it's right-hand limit. Okay, so you would just say the limit of f of x as x approaches c from the right. So it's not to the left, it's from the right, which indicates that it's positive, positive superscript. Then this one's left-hand limit, the minus, and this just means you're approaching from the left. Okay, sometimes the limits can be different. This is a classic graph. This is called the greatest integer function, and it's also called the step function, and this kind of stuff is very important in calculus. If you really were to draw these over and over, off to infinity, if you were to continue the steps, then this would be basically a piecewise function with an infinite number of parts. So it really just needs its own symbol, because we can't write piecewise function with infinitely many parts in it. So we would actually just use its own abbreviation. So INTX. And INTX is actually one of your functions that your graphing calculator does know. So you're welcome to test it out. You can try graphing it. Just go under catalog and you should be able to find the actual function built in. Okay, so let's just pick a value. Let's say x equals 2. And we'll look at the graph and we'll do a left approach and a right approach. Actually, we'll do a right approach first and then a left approach. And we'll see what we get. Okay, so let's zoom in. We're going to be doing a right approach. And this is for the number 2. Okay, so as we approach from the right, actually it looks like these are 3s. Sorry about that. Let's go back and fix these. Our graph is drawn with an approach to the number 3. Okay, maybe you can see that already. We'll look at the picture together. Okay, sorry about that. Let's go to our graph. Okay, so it looks like we're approaching 3 from the right. Okay, now of course we're on the graph following. So we're coming inward this way. And we don't need to go all the way to x equals 3. We're supposed to be approaching it and asking what y value are we getting closer to. Well, it's kind of a dumb question. I mean, we're on this line. This is the y equals 3 line. So we're just simply on the 3. And so we're approaching y equals 3 too, in a sense. Okay, so the answer here is 3. Okay, on the other hand, if we're coming from the left side, even though we're approaching the same x value, we're traveling on this piece of the graph, and although the function isn't actually defined at x equals 3, we're still approaching this empty hole whose y value is 2, actually. So we have to come over here and write 2. And since these disagree, we would have to just say that the limit doesn't exist. The general limit. So if you take off the superscripts and you just discuss the limit as x approaches 3, and we'll change this to a 3, we would put d and e. Okay, so when there's no plus or minus indicated, we're really being asked for a two-sided limit. And so having done the two one-sided limits, and discovering then that they didn't agree, we would just write D and E. In other words, the left and right limits for x equals c, they really must be the same value on either side in order for a function to be evaluated, in order for a limit to be evaluated at a specific, or I should say, in order for a limit to exist at a certain point. Okay, so this blank, I made that blank there. It's just a statement here, nothing to fill in. Okay, let's take a look at one-sided and two-sided limits. This theorem down at the bottom. The function has a limit as x approaches c if and only if the right-hand limit and left-hand limits at c exist and are equal. So I just restated it up above. So let's go and write that. If I ask you for the limit as x approaches c, you're really supposed to split that into two questions, right and left. If the one that you've evaluated on the right side and the one you've evaluated on the left side are equal, then this is the value of the limit. So this is a statement of existence. If this came out to be L, let's say it came out to be 5. We'll just call that the number L. Then this would be L, and this would be L, and this would be L. So they're all equal. So the existence depends on both sides being equal. And then we could call the answer L. It would be the limit on the left, it'd be the limit coming from the right, it'd be the limit coming from the left, it'd be the limit in general. It would just be L, all of it. And of course it's a number if you're dealing with the problems we've been dealing with. It can also be an expression if numbers are absent from the problem, but that's not what we're working on. Okay, here it is. So we have a limit as x approaches, okay, and you can see the little subscript there. It's -1, and the plus means from the right of the function equals 1. Okay, is that true? Let's look at -1. Let's look at -1 here. Now it's an x, right? So we're looking at x equals -1. We're actually approaching it from the right. Okay, so we're right here, moving along. Moving inward, moving inward. What is the y value of approach here? Sure enough, it's 1. Okay, so this is true. True statement there. Okay, let's study x goes to 0 from the left side. Does it equal 0? Well, yeah, if you're coming from the left side towards x equals 0, the graph is indeed approaching y equals 0. So this is a true statement. Okay, is it true that approaching 0 from the left and approaching 0 from the right are equal limits? Well, we just did the left side and we saw that the graph is indeed dropping down onto y equals 0, and it turns out on this side, although it's different shape, and this point right here is an interesting one. Whether the point there exists or not, we do have we have an agreement on the point of approach. So this is actually true. So far they're all true. Okay, this next one, we're approaching +1, so this is just a regular 1, and from the left. So don't think of this as -1. This is 1 from the left. Let's see if that really is 2. Okay, we're approaching x equals 1. So 1 is down here. Okay, so we're coming in this way. Here we go, up the curve, yes, we're approaching y equals 2. Turns out there's nothing there, but that's our approach anyway. So this is true. And here we're coming from the right now. Okay, this is not true. As we come from the right, we're on this portion of the piecewise function, and we can see that the y value of approach here is actually 1. not 2. So the left side rises up to 2, but this side, as we come inward, we find ourselves at y values which are equal to 1, or you could say approaching 1, except that they're equal to 1. So special case there, and this is a false. Okay? Okay, let's look at this general statement that the limit of f of x as x approaches 1 doesn't exist. I would agree with that. These two are not true, or excuse me, they're not, and so we would say then, and I'm sorry, yeah, they're not equal, because this is true and this is false. So then we would say that this is true statement here. Okay, the limit as x approaches c for the function f of x exists at every c value within the realm of 1 to 3. Now remember, this is interval notation. It means 1 is less than x is less than 3. It does not mean 1 comma 3. Oh, I wrote that here. Okay, good. So, is it true? Well, let's take a look. If we're in this realm and we're traveling, let's say, to 1.3, you can see that there's a limit on either side, the two arrows being the two directions traveling along the graph. They come together towards the same point in the middle, whatever that is. And this happens everywhere. It even happens here, this being the most interesting spot on the graph, I suppose. You come in from this side, you come in from this side, either way you're approaching y equals 1. This point has nothing to do with the limits question. So that's just there to throw you off. Alright, so it turns out that there is a point, or I should say agreement, on any two opposing arrows there. They come together towards the same y value. And so let's go ahead and put a true on that last one. And then that concludes the true-false section there for example 3. These are really good questions. They force us to really think about the meaning of limits, and having the graph to look at is a real luxury, just so you know. Okay, but it's a good training exercise. So that's really the lesson itself, and you'll be just going down here and writing in again the things you want to memorize. I think that integer function is definitely worth memorizing. Special cases, one of the ones that we learned was that if you're doing a limit of a constant, that was the very first rule, it just comes out to be that constant. That's special in a way. Yeah, I made a couple of sentences there at the bottom. Okay, very good. So next up will be lesson 2.2.